What's up everyone? So let's continue from what we left off from the last video. In the last video, we found the expression 3k squared minus 3k plus 1 being the expression of the nth term of the sequence such that the partial sum of the sequence will be equal to n cubed. And we're saying that this expression is actually a little bit special, and we can actually find another way to find out such expression, and we actually can use that idea to help us to find the expressions for higher power as well. So before we actually talk about the expression, let's look at the two known facts and see what we can actually get. Well, if we look at the n squared part, this term is in fact a little bit special because if we think carefully, this is actually looks very similar to the tail part of the expression of k minus 1 quantity squared. What's that? So if we look carefully, k minus 1 squared is actually equal to k squared minus 2k plus 1. And again, you can use binomial expansion to help you to get the coefficients of each term. And if we look at the expression that we actually found last time, this expression is also very special because if we look carefully, it is actually very similar to or very close to the tail part of k minus 1 cube. So you can check it here. The quantity k minus 1 cube is equal to k to the third power minus 3k squared plus 3k minus 1. So the only difference between what we have in our expressions of the nth term and the tail part of the expression of k minus 1 to the higher power is just the parts that we have a negative version of it, and we just need to take the leading term away. So maybe here is our claim here for even higher power, which is in order to find out the sequence, the expressions of the sequence such that the partial sum is equal to n to some higher power, let's call it n to the r power. And of course, in our situation, r will be some natural numbers. Okay. So again, r could be 4, 5, or something even higher, but not assuming to be fractions or something irrational yet. Okay, so we will say that in our expression here, this will be the tail part the tail of the expression k minus 1 to the power. That's the same as the power of the right hand side, which is k minus 1 raise it to the rth power. And again, this is not done as we notice that the tail part is actually a negative version of what we want. So how can we fix that? We can just put a negative sign here. Okay, the negative version of the tail parts. So how can we actually check the claim? Here's what we are going to do. We're going to use this idea here, and then to show and then to derive the right hand side. So here is the proof. We're saying that the sum of the negative version of the tail part, okay, of k minus 1, okay, to the alpha power is in fact just the negative version of what we have seen in here. The the tail part of k minus 1 is everything except missing the leading term, which is k to the alpha power. So we can just try to add we can just try to add k to the alpha power into our expression, such that we get k to the alpha power and then minus k to the alpha power. And again, this is legal because first of all, we have finitely many terms. So if we have some constants or some numbers adding together with only finitely many terms but not infinitely many terms, we will still have some values ending up, meaning that it's converging and it's not gonna blow up into infinity. And that's why we are allowed to add and subtract 0 without actually changing it. And again, that also means that no matter which order of terms we're adding and subtracting, we can, let's say, add the first odd terms and then add the even terms later. It will still end up with the same result as we just follow it regularly. Okay, so we have the tail of the k minus 1 to the r power terms. All right, good. So maybe I should just put brackets here so that you know that everything is inside of the summation. Then we're going to put this k to the r power term into here, so that if we're trying to combine the two together, we will be able to get minus of k to the r power, which is from here, and then we have the tail part, which is here. This is the negative version of the and this expression is same as the negative version of k minus 1 to the r power, which is the tail part. Meaning that if we put them together, this here will be adding the tail part of k minus 1 to the r power. Good. So if we think carefully, this expression starts off with negative k to the r minus 1 power, and then here are some constants here. Let me use C1. Okay, and then we will end up with the tail part will become this, and then minus so on and so forth. Then as we combine it with the leading term k to the r power, this whole thing together will then be complete and turns into just k minus 1 to the r power if we look at the whole expression. So that will give us the sum when k starts from k equals 1 all the way up to k equals n of k to the r power minus k minus 1 to the r power. And again, as a finite sum is converging, meaning that we are allowed to rearrange the order of the terms and without changing the total value of the terms, of the total value of the sum of the terms. So since that is allowed, we can now break this back into two summations. We can have the first part will just be the sum of k to the r power minus the second sum, which is k minus 1 to the r power, like this. And here is what we end up with. Since this is starting from k equals 1 to k equals n. We can just list them out, or we can just think it like this. Let's list them out. We have 1 plus 2 to the r power plus 3 to the r power. Maybe I should put the r here as well. Plus all the way down to n to the r power. Minus, here k starts from 1, but we actually have a shift that we need to actually get 1 less than. So in fact, our first term will then become 0 to the r power, and then the second term will now become 1 to the r power, so on and so forth. Then what's the last term? Last term is, of course, n minus 1 to the r power. So this is what we're going to have. We're going to subtract, let me put a minus sign here. Subtract. First term is 0 to the r power, and again, I'm going to write like this, like how we did in vertical subtraction in elementary school. So we have 0 to r power plus 1 to r power plus 2 to r power plus all the way down to here, n minus 1 to the r power. Now, what can we do? If we comparing from the top and bottom, we see that there are things that can be cancelled out. In fact, we can cancel out the 1, we can cancel the 2 to r power. It's not written here, but there's still a 3 to r power, so we can cancel that out. And then all the way down to, again, it's not written, but it's still there, n minus 1 to r power. Now, can we cancel the n to r power? No, because there's no n to r power on the bottom. So this is also known as a telescoping method, which is very useful when we do the summation of sequences. So that now everything is everything in the middle will be cancelled out. Only the beginning and the end will still be remaining, so that we end up with the end of the first row, n to the r power, minus the first term in the bottom row, which is 0 to the r power, or 0, which is equal to, of course, n to the r power. And therefore, we just prove what we have claimed. We can always try, we can actually find out the expression of the am term of the sequence easily, and also using a clever method, so that when we add the first n terms together, we will end up with n to r power without actually using the tools that we have done in the previous video. That's it. I hope you all enjoyed this video. If you like, and please don't forget to like, and you can also subscribe to my channel so that you will be able to find out more of my other videos. Don't forget to turn on the notification so that you won't miss any of my new videos when it is up. And I'll see you guys in the next video.